Hi class, I'm making this video to help you get started with the classification process that you are going to have to do for exercise 8 and perhaps in the final exercise as well, this unsupervised classification or clustering. So what I'll show you is how to filter the county data to pull out Worcester County, and then how to generate and interpret the clusters, maybe to get ready to extracting areas for those. So let me see, where am I? Go to the Earth Engine tutorial page, unsupervised classification algorithms, also called clustering, and we'll grab their sample code for an area of Egypt. Let's see what this does. There are two layers in the map, one called clusters, one called region. Region, we see, is a rectangle painted onto an image, and the rectangle is defined by kind of minimum and maximum Latin long. The image clusters is going to be the result of the clustering process, that unsupervised classification. So the input it takes up here, variable input, is an image object. It's Landsat 7 top of atmosphere reflectance from 2001. So it's kind of an annual composite product representative here. Maybe what we can do, helpful, is map add layer input. We'll have to tinker with that a bit. We'll change the band 4, band 3, band 2. Let's see how that works. Just to try to get something legible. There we go. So that's something like a true color composite of that year 2001 top of atmosphere reflectance for this Nile River Delta. Region, that's a rectangle just around it. And how is that used? It's used in making the training data set. So this region is being sampled. 5,000 pixels are kind of randomly chosen within it. And then the spectral characteristics of those pixels. How is it reflecting blue light? How is it reflecting green, red, near infrared light, and so on? Being used to allocate or group each pixel, not just the sample, but everything within the rectangle, really everything in the input image, into one of 15 classes. So it's WECA K-means 15, training. Result is going to be that clusterer applied to the input image, and then we add that with a random visualizer showing these different colors to generate this clusters output. So there are 15 different colors in this image, different groups that pixels have been allocated into, and they should make somewhat good sense for this Nile River Delta area. If we zoom out, we can see that all the pixels everywhere on the terrestrial surface of the Earth were classified. The classification probably isn't going to make sense very far away as you move to different types of regions. As we zoom in, we'll see some things that help us interpret the output. So if we flicker on and off this clusters layer, you can see that certain categories, certain colors will cover the agricultural land and others the sand. So this pink, here I have the inspector, is cluster 0. This light yellow, oh, I'm sorry, the light yellow should be cluster 9. If we go out into some of the desert areas, this deep brown, cluster 3, cluster 6. And so using 15 clusters, we're actually seeing variation in the desert, in the agricultural land that we might not really know how to make sense of. But we can simplify our output by reducing this number, or making it smaller, I should say. I'll cut it in half about, run for 7. We run it again. And here we have a lot fewer categories, and they're somewhat easier to make sense of. So the water here is light pink. What we're seeing is cluster 5. That this kind of, I don't know, yellowish sand. Cluster 3. The generic farmland in magenta. Cluster 0. And then I think it's developed land around here. We zoom in. Oh, it's more farmland. We can see it as green. Cluster 1. So with 7 clusters instead of 15, it's easier for us to interpret the output here. There's a clear difference between sand and field and water for the most part. So it's a good area to kind of target. Now relating this to Worcester, where we can also kind of pick out some categories a little bit easier. A way to adapt this is, well, we're going to get rid of this set center method. We don't need to see Egypt every time. And we're going to need to specify a different region. And an easy way to do that, I guess, counties, import. We can do it here. So we'll do counties dot filter. And I'll use an equivalence filter. Put up and drop to the bottom here. Put 2 things in quotes. And as I mentioned in the Word document, don't use the name field. Use the one called GOID. And we can find out more about this by looking at the data page, the table schema. You can see the name of the properties, GOID. They have a name, but as I said, there's more than one Worcester County in the US. We'll use this GOID, a county identifier. Oh, so let's see, GOID. And the question is, what value? What's the specific value of that field that we want to see? So map, add layer, add in counties, we'll run it. Oh, still in Egypt. Cut over to the US. Here we go. Start to see them. Pretty dark right there. But with the inspector, we'll click Worcester County, where we want to be, right here, Central Mass. And we'll look, Objects, Layer 1, Feature Collection. There's a feature. Look at its properties, and we'll scroll down to that GOID. It's 25027. That's the number I'll put right here, their region. And instead of adding all the counties, I'll just try adding region, see if it worked. And it did. So that's our Worcester County. Get rid of this. The rest of the code's already running. So remember, I kept the variable name, I just assigned it a different geometry, that of Worcester County. If I scroll down, it's still being used to select the 5,000 pixels that define how all the other pixels are being grouped. I'll actually add this to the map after so we can see it. There we go. So still from the Egypt exercise looking at 7 categories. We'll zoom in here to Worcester. Comment that one out. So here's Worcester. I've got the satellite base map on with the labels off. I'm zooming into the city. Clark's down here. This should help us interpret our output. And turn in clusters. And you might find yourself turning it on and off against the satellite data to try to interpret things. Just based on these colors, we'll start to think about what we see in this landscape and what kind of colors we can assign to it. Water is a good place to start. Here's Lake Quinsigamon. Turn it on, we see that kind of magenta-y color. If I click on it with the inspector, that's going to show up as cluster 0. And when you do this, it's a good habit to have a piece of paper next to you or the notepad application open and just keep track of what the cluster number is for each of your important information classes. Water may or may not be one of them. For us, we just care about forest, so we don't really need to write down water is cluster 0. Good to know, though. We look kind of downtown Worcester, all those built materials. Let's see what colors are there. I can see the bright white building tops are showing up black. So that's cluster 4. Again, if we care about forest, we don't need to remember that, but good to identify things. We look over by the airport, see some black, some of that light pink too. Light pink. Cluster 5, that seems to be a combination of built materials, maybe some vegetation in there too. Looking here, the yellow, kind of honey mustardy yellow. Cluster number 2. We look in the satellite image, that looks to be open fields. So the area around the airport runways, Green Hill Park up here, maybe some farms over west of Worcester. So we don't need that. Enough of what we don't need. Let's move to the west a little bit and think about what covers forest. So forest deep green in this area. Even just click on it. We're seeing cluster number 1. It looks like this light brown, dark brown, and green. Note these are just random colors. Light brown, dark brown, and green. That seems to be what we need for forest. So just like in Egypt, when we were using 15 as the number of clusters we wanted, it was calling the sand kind of 4 or 5 different clusters. And that kind of level of distinction may not be helpful for us. Here we're getting forest as 3 different colors. That may or may not be important, but it's a small enough number that we can just keep track of those numbers. So let's see. Turn on the cluster. Light brown, that's cluster 6. This kind of darker brown, cluster 3. And that green is cluster 1. So we have 1, 3, and 6. 1, 3, and 6. So we'll remember that. So we have this result, what we're adding to the map and calling it clusters here. If we print result, we can see in the console that it's a one-band image, and it has just those integers describing the cluster. So result is an image, and we can use mathematical operators or relational Boolean operators to produce an image based on just certain classes. So let's see. Mathematical operations here back in the Earth Engine guides. That may be the best option. We'll go back to our code. So we'll generate a new one called var forest equals, and I'll write down the numbers that we need here. We want to start with result, and then we can use a .eq filter to just grab one. Let's add that to the map, see what it looks like. Map add layer forest. Internal error has occurred. Let's see. An internal error has occurred. We'll just try it again. There we go. Keep trying until something works. So here, this forest is also an image. It's a Boolean image, so white a value of 1, black a value of 0, where the category in the cluster, or the cluster number, was 1. If we turn that on and off, we see it gets all of the green. And we also wanted the light and darker brown, category 3 and 6. So we just make this a little bit longer. .or result.eq3. We'll run that again, see how it works. So now we're pulling out the green and I think the light brown. There we go. Dark brown. Anyway, going to add in, one more of these .or. So here we go. We got a long line of code here, but now that it runs, looks like we're getting all of our forest. And yeah, so there's the Wachusett Reservoir, there's Quabbin Reservoir, here's Worcester as an urban area, kind of Framingham into Boston. And zoom in. If we zoom into Worcester, we see that a lot of these white pixels do cover residential areas. So understand it's not a super duper accurate classification, where if there's some tree cover, areas are being classified as forest. So it looks like this is going to be an overestimation of forest land, but it's a good enough product. And so then for the county, the exercise asks you to extract the area, and it gives a link to this tutorial on global forest change, in which we did that. Quantifying forest change. If we scroll down, you can see here, get a reducer. So sum the value of forest loss pixels in the Congo Republic. So what we'll do is copy that over, just those lines. We still want a sum. We're not working with loss image. We'll work with forest. Geometry, it's not going to be Congo. It's going to be what we call region. And then the scale is 30. Print out that stats. So 48, what is that? 4,800,000 pixels. So if we want an area, we figure out the area of each pixel. It's a Landsat scale or 30-meter pixel. So you can just use the number 900 square meters, and you'd multiply 900 times this to come up with an estimate of the area of forest in Worcester County. So note there's nothing official about 7. You might find it easier to work with fewer or more categories, depending on the number of categories that you have, or even maybe the random outputs of this process. Numbers 1, 3, and 6 might not apply to you. Say they were 2, 3, and 8. You'd keep that structure, just change the different ones here, the specific numbers. And then note we're using 2001 as an input. So when I was trying to judge what the map clusters were compared to the satellite image, note that there's about a 20-year gap between the more recent satellite base map data and that 2001 Landsat input. And so working with year 2018 data, you should be able to it should more closely correspond to what you're seeing in the satellite base map. In Worcester, that's not a huge problem. There has been substantial forest loss since 2001, kind of suburban or peri-urban development, but it's not the kind of scale of expansion you'll see in other parts of the US or other parts of the world.